It's one of the biggest questions out there. It's also one of the newest. For most of human history, we looked up at the stars and assumed everything was fixed. A perfect, unchanging clockwork. Then, about a century ago, we learned the universe was growing. Galaxies were flying away from each other, space itself was stretching, and for decades, we thought we knew the next part of the story. We assumed the expansion was slowing down. It had to be. Gravity is the boss of the cosmos. Everything with mass pulls on everything else with mass, all the stars, all the galaxies, all the invisible dark matter, they're all pulling on each other. That constant tug should be acting like a brake on the expansion. The universe should be getting tired, slowing its sprint. The only real question was whether it would slow down forever, or eventually stop and fall back in on itself in a big crunch. But the universe had a surprise waiting for us. In the late 1990s, two separate teams of astronomers were trying to measure this exact slowdown. They were using some of the most powerful telescopes on Earth to look for distant exploding stars. These explosions, called Type Ia supernovae, are special. They act as cosmic light bulbs. They all have roughly the same actual brightness, so if you see one that looks dim, you know it's far away. If it looks very dim, it's very, very far away. By measuring their dimness, you can figure out their distance. They also measured the light from these supernovae in another way. They looked at its color. Just like the siren of an ambulance sounds higher when it's coming toward you and lower when it's moving away, light does something similar. Light from a galaxy moving away from us gets stretched out. The waves get longer. This shifts the light towards the red end of the spectrum. It's called redshift. The more redshifted the light, the faster the galaxy is moving away. So the plan was simple. Find these supernovae, measure their distance from their brightness, measure their speed from their redshift. By looking at supernovae at different distances, you're also looking back in time, since the light took billions of years to reach us. This lets you map the expansion of the universe over its history. They expected to see that the expansion was faster in the past and is slower now. They were going to measure the cosmic deceleration. They didn't find it. Both teams, working independently, found the opposite. The most distant supernovae were even dimmer than they were supposed to be. They were farther away than the models predicted. For them to be that far away, the expansion of the universe couldn't have been slowing down. It must have been speeding up. This was a shock. It was like throwing a ball into the air and watching it shoot into space instead of falling back to your hand. It went against everything we thought we knew about gravity and the fate of the universe. The discovery was so profound, so unexpected, that the leaders of those two teams won the Nobel Prize in physics for it. They had found that the universe is not just expanding. The expansion is accelerating. So, why? What could possibly be powerful enough to overcome the collective gravity of everything in the cosmos and push space itself apart faster and faster? The honest answer is, we don't know for sure. But the leading idea has a name: dark energy. It's a strange name, and it's a bit of a placeholder. It's called dark because we can't see it. We can't detect it directly. It doesn't interact with light or matter in any way we can measure. We only know it exists because we can see its effect. We see the universe accelerating, and we need something to explain it. Dark energy is the name we give to that something. It's less of a discovery and more of a label for a mystery. But we do have a primary suspect for what dark energy might be. It's an idea that goes back to Albert Einstein. When Einstein first developed his theory of general relativity, the theory that describes gravity, his equations show that the universe should be either expanding or contracting. It couldn't just sit still. But at the time, everyone, including Einstein, believed the universe was static. And it had always been and would always be. To make his equations match this static universe, he added a little something extra. He called it the cosmological constant. It was a kind of energy that was part of the fabric of space itself. An intrinsic energy of the vacuum. This energy would have a strange property. It would create a sort of anti-gravity, a repulsive force that pushed space apart. He tuned it just right so that it would perfectly balance the pull of gravity, resulting in a static universe. Then, a few years later, the astronomer Edwin Hubble proved that the universe was, in fact, expanding. The galaxies were all moving away from us. Einstein's original equations were right all along. He didn't need the cosmological constant. He supposedly called it his biggest blunder and threw it away. Maybe he was right for the wrong reason. When astronomers found that the expansion was accelerating, they looked back for something that could cause a cosmic push. And there it was, sitting in Einstein's old equations, the cosmological constant. What if it exists after all? Not to create a static universe, but as a real property of space. Here's how it would work. Imagine the universe is a giant expanding box. Inside the box are galaxies and dark matter. As the box gets bigger, the matter inside gets spread out, its density goes down. So the gravitational pull of that matter gets weaker over time. It's like a crowd of people in a room. When the room is small, they are all close together. When the room expands, they spread out. Now, imagine that empty space itself has energy. The cosmological constant says that every cubic centimeter of space has a tiny, fixed amount of this energy. It's a fundamental property of the vacuum. As the universe expands and more space is created, more of this energy comes into existence. Unlike matter, its density doesn't go down, it stays constant. In the early universe, everything was packed together tightly. The density of matter and dark matter was very high. Gravity was king. The pull of gravity was much, much stronger than the tiny push from this vacuum energy. So, for the first several billion years of its life, the universe's expansion was slowing down just as everyone expected. But as the universe kept expanding, the matter kept getting more and more diluted. Its gravitational grip grew weaker and weaker. The dark energy, on the other hand, stayed just as strong as it always was, because its density is constant. More space meant more vacuum, which meant more total dark energy. Eventually, about 5 or 6 billion years ago, a tipping point was reached. The relentless constant push of dark energy finally became stronger than the weakening pull of gravity. The brakes came off, the cosmic accelerator was pressed, and the expansion of the universe started to speed up. This is the standard model of cosmology right now. It's called the lambda CDM model. Lambda is the symbol for the cosmological constant, and CDM stands for cold dark matter. It says the universe is made of about 5% normal matter. The stuff we see, about 25% dark matter, the invisible stuff that holds galaxies together, and a whopping 70% dark energy, the mysterious stuff pushing everything apart. This idea fits the observations of the accelerating expansion perfectly. It also fits with other observations we've made of the cosmos, like the leftover heat from the Big Bang, known as the cosmic microwave background. It's a pretty successful theory, but it comes with a huge glaring problem, a really big one. When physicists try to calculate how much of this vacuum energy there should be based on our understanding of quantum mechanics, they get a number that is wildly, absurdly wrong. The theoretical prediction for the energy of the vacuum is about 10 to the power of 120 times larger than what we actually observe. That's a 1 with 120 zeros after it. This is not a small error. It has been called the worst theoretical prediction in the history of physics. Nobody knows why there is this massive disagreement. It means that either our understanding of quantum physics is deeply flawed, or the cosmological constant isn't the right explanation for dark energy, or there's some other physical principle we don't know about that is canceling out almost all of that energy, leaving just the tiny bit we see today. This discrepancy is called the cosmological constant problem, and it's one of the deepest mysteries in science. It tells us we are missing something fundamental about how the universe works. Because of this problem, and just because it's good science to explore all the options, scientists have come up with other possible explanations for the cosmic acceleration. One alternative is called quintessence. This is another form of dark energy, but unlike the cosmological constant, it's not constant. Quintessence is imagined as a dynamic, changing energy field that fills all of space. Its strength could change over time and could be different in different places. Think of the cosmological constant as a simple thermostat set to one temperature forever. Quintessence is more like a weather system with high and low pressure zones that can shift and evolve. This idea is attractive because it avoids some of the theoretical baggage of the cosmological constant. It doesn't have to be the energy of the vacuum itself, it could be something new. If dark energy is quintessence, its behavior could change in the future. It could get weaker and the acceleration could stop. It could even become attractive, causing the universe to collapse after all. Or, in a more exotic version called phantom energy, it could get stronger and stronger over time. This leads to a wild scenario for the end of the universe called the Big Rip. In this future, the accelerating expansion would become so powerful that it would eventually overcome all other forces. First, it would tear apart clusters of galaxies. Then it would rip apart the Milky Way itself. Then it would pull the Earth away from the Sun and the Moon from the Earth. In the final moments, it would be strong enough to overcome the forces holding atoms together, and the entire universe would be torn into its fundamental particles. It's a dramatic idea, but one that is possible depending on what dark energy turns out to be. There's another, even more radical possibility. What if there is no dark energy at all? What if the problem isn't a mysterious substance pushing the universe apart? What if the problem is our understanding of gravity? Einstein's theory of general relativity has been tested and confirmed with incredible precision within our solar system and in many other astronomical situations. But we've never tested it over the largest possible scales, the scale of the entire universe. It's possible that over these immense distances, gravity just doesn't work the way Einstein said it does. These ideas are called theories of modified gravity. They propose that gravity itself has a built-in repulsive aspect that only shows up on cosmic scales. In this view, there's no dark energy. The acceleration is just a new feature of gravity that we're only now discovering. This is a very difficult path to take because general relativity works so well everywhere else. Any new theory of gravity would have to look exactly like Einstein's theory on smaller scales, like in our solar system, but behave differently on the scale of billions of light years. It's a tall order, but scientists are exploring it. If it's true, it would be an even bigger revolution than the discovery of dark energy. So how do we figure out which of these ideas, if any, is right? How do we solve the mystery? The answer is to gather more data. Lots more data. We need to create a much more detailed map of the universe and its expansion history. Astronomers and physicists are building massive new experiments to do just that. There are new space telescopes, like the European Space Agency's Euclid mission and NASA's upcoming Nancy Grace Roman Space Telescope. They will survey huge swaths of the sky, measuring the positions, shapes, and distances of billions of galaxies. By looking at how galaxies are clustered together throughout cosmic history, they can trace the battle between the pull of gravity and the push of dark energy. One of the key things they look for is something called baryon acoustic oscillations. It's a complicated name for a simple idea. In the very early universe, before stars and galaxies formed, the cosmos was a hot, dense soup of particles and radiation. Waves of pressure, like sound waves, traveled through this soup. Then, the universe cooled enough for atoms to form, and these waves became frozen in place. They left a faint imprint on the distribution of matter. We see this imprint today as a slight tendency for galaxies to be separated by a specific distance, about 500 million light years. This distance acts as a cosmic ruler. By measuring how big this ruler appears at different times in the universe's history, we can measure the expansion history with incredible precision. Scientists are also using a technique called weak gravitational lensing. According to Einstein, massive objects bend the fabric of space-time. So, the light from distant galaxies gets slightly distorted as it passes by other galaxies and clumps of dark matter on its way to us. By measuring these tiny distortions across the sky, we can create a map of all the matter, both visible and dark, in the universe. This tells us how gravity has been clumping things together over time, which gives us another way to test the influence of dark energy. And of course, we are still looking for more supernovae. Projects like the Vera C. Rubin Observatory in Chile will scan the entire night sky every few days, discovering thousands of new supernovae. This will give us a much more detailed record of the expansion in the more recent past. The goal of all these projects is to measure the properties of dark energy with extreme accuracy. Is it perfectly constant, like Einstein's cosmological constant, or has its strength changed over time, as quintessence would suggest? Even a tiny change, a 1% deviation from being constant, would be a monumental discovery. It would rule out the simplest explanation and point toward new physics. It would tell us that dark energy is not just a property of empty space, but something dynamic and evolving. We live in a strange moment. We have a standard model of the universe that works remarkably well, but it is built on two pillars of almost complete ignorance: dark matter and dark energy. Together, they make up 95% of the universe. All of human history, all the stars and planets we have ever seen, are just the 5% of fluff on top of a deep, dark reality we are only just beginning to perceive. The discovery that the universe is expanding faster is not just an interesting piece of trivia. It's a clue that points toward a fundamental gap in our knowledge. The solution could rewrite our understanding of space, time, and gravity. It could reveal new forces of nature or new particles we never imagined. Or it could confirm that the very vacuum of space is filled with a bizarre energy that is slowly but surely pushing our universe toward a cold, empty future. We started by thinking the universe was static. Then we learned it was growing. We assumed it was slowing down. We discovered it's speeding up. Each step has been a surprise, a humbling reminder that the universe is far stranger and more wonderful than we ever imagined. The reason it's expanding faster is because of a mysterious force we've named dark energy. But what that really is, why it's there, and what it means for our ultimate fate are Questions that are driving the next great adventure in our quest to understand the cosmos. The answer is out there, hidden in the light from distant galaxies waiting for us to find it.